Have you ever just stopped and thought about how wild it is that we learn to talk? I mean, really think about it. It's maybe the most complicated thing we ever learn to do. We go from just making noise to telling jokes and arguing about movies. So today, we're going to unpack that incredible journey of how our brains literally build language from scratch. And it all starts with something you've probably heard a million times. A little kid saying something like, "I gooed to the park." Sounds kind of cute, right? A simple mistake. But what if I told you it's not a mistake at all? It's a clue, a breadcrumb, leading us to something brilliant happening inside their brain. And that's our big question for today. Why do kids talk like this? Is it just a random flub? Or is their brain up to something way, way more interesting? I think you know the answer. Unlocking this little puzzle reveals the secret to how we all learn to communicate. So let's treat this like a little mystery. Our first stop is looking at this so-called curious mistake. Because by solving the case of "I gooed to the park," we're actually going to uncover the hidden machinery that gets language up and running in all of our heads. See, here's the key. You got to reframe the whole thing. These little errors aren't failures, they're signs. They show us that a kid's brain isn't just a sponge passively soaking up words. No, it's an active detective hunting for patterns, trying to crack the code of the language it hears all around it. So for the brain to crack that code, it needs some tools, right? Well, let's pop open the language toolkit that every single one of us is born with. First up, we've got phonemes. These are the absolute smallest units of sound. Think of them like individual notes in a song. The tiny puff of air that makes a puh sound versus the vibration of a buh sound, that's a phoneme. It's the difference between pat and bat. And what's totally wild is that babies are born able to hear and distinguish pretty much every phoneme from every language on Earth. It's incredible. Okay, next up are morphemes. Now, if phonemes are the sounds, morphemes are the smallest chunks of meaning. I like to think of them like Lego bricks. You have a main brick, like play. Then you can snap on other little bricks, like ing, to make playing, or id for played. Even a prefix like un is a morpheme. Each little piece carries its own meaning. So you've got your sound notes and your meaning bricks. Now how do you put them together? Well, that's where syntax and semantics come in. Syntax is just the rules about word order. The cat sat on the mat works because it follows the rules of English syntax. Semantics, on the other hand, is all about whether it actually means something. You could say, "The mat sat on the cat." The syntax is perfect. But, the semantics are a little strange. And the thing that holds all of this together, that's grammar. Grammar is the master blueprint. It's the entire shared system that tells us how to combine our phonemes, morphemes, and syntax to make, well, basically an infinite number of sentences that we can all understand. It's the operating system for our language. All right, we've got the toolkit. Now let's watch how a child actually puts it to use. This next part is all about that amazing journey from simple babbling to full-on sentences. It all kicks off around 4 months old with babbling. And that's not just random noise. It's the brain warming up, playing with all those phonemes. Then, boom, around age 1, they hit the one-word stage. A single word can mean a whole sentence. Ball can mean "I want the ball" or "look at that ball." Then, around 2, syntax shows up with the 2-word stage. Things like "want juice," "daddy go." You can just see the complexity exploding. And this is so important because it proves this isn't just about copying what they hear. A child isn't a parrot. They are actively, piece by piece, building a powerful communication engine inside their own head. And they're doing it at a speed that is just mind-boggling. Okay, now we have the toolkit and we have the timeline. We are officially ready. Let's go back to our original clue and finally solve the mystery of "I go to the park." So here it is, the big reveal. That little phrase that we all assumed was just a simple error. It's not. In fact, it's the exact opposite of an error. It's proof. It is solid gold evidence that the child's brain has had a huge breakthrough. It means the detective has found a major clue. It has successfully identified a core rule of grammar and is now applying it with gusto. There's a name for this, of course. Scientists call it overgeneralization, and it's exactly what it sounds like. It's when a brain learns a powerful new rule and gets so excited about it that it just generalizes it to everything, even to the words that are exceptions to that rule. So think about it from the kid's perspective. Their brain finally figures out, aha, to talk about something that already happened, you add the id sound at the end. Walk becomes walked, jump becomes jumped. This is a game changer. So logically, the brain applies its awesome new rule to everything. Go must become good. The same thing happens with plurals. The rule is add an S, so one mouse becomes two mouses. It's perfectly logical. And here's the kicker, the part that's so cool. Saying goed is actually a more advanced step in language development than just saying went. Why? Because at first, a kid just memorizes went by copying adults. But saying goed proves their brain has moved past simple memorization. It's figured out the system. It's a rule maker now, not just a word copier. And that just leaves us with this one kind of huge final thought. If our brains are this powerfully hardwired to find patterns and rules in language, what other patterns are we built to find in the world? This drive isn't just for talking. It's how we make sense of, well, everything. Social rules, music, science, you name it. That cute little mistake a kid makes is actually a window into the very essence of the human mind, a brilliant, relentless pattern-seeking machine.